but that means I don't have all my hands free to gesticulate. You know, natively I'm Italian, so we need to move our hands. It's something that comes with the package. So, what are we talking about today is gravitational waves. Gravitational waves are damn difficult. They're a prediction of a theory by a madman called Albert Einstein. They're part of his theory that been predicted long ago. It's about 100 years ago. And thanks to an incredible set of technological advances, we were finally able not only to detect them, but to observe all the astronomy and cosmology that creates them, and find that things that have been only true in mathematics or true only in some indirect observations like black holes are true. They exist. They vibrate through space-time, and they're so powerful that we detect the vibration all the way to us. But let me go stepwise. So today, let me just introduce quickly and rephrase what you've seen already. Well, how do we do astronomy normally? How do we do to see stars and to see galaxies? Why do we say see things? It implies that the main detector is your eyes. Okay, and what's the implication? But then general relativity, and you're experts now because you've had one class on special relativity and one class on general relativity, so you know much more than I do, and I should be the one asking questions, right? GR tells us that we can build different types of observatories based on these gravitational waves I'm going to tell you about. And then we have a dream. The dream is going to space, building a big observatory up there, and there's many reasons to do that, and I'll hope to clarify why and how. And I'll tell you a bit about the future, and then get any questions of yours. I'll try to go slow, like I said before. If any of you really don't get what we're talking about, you raise your hand and say, hey, Misha, I don't understand. Stop, danger, please. This is a school. We all have to learn, okay? Now, suppose you sit down. You're in front of, well, in this case is a bridge in New York, right? I did not have one on the Moskva. I'm sorry, I've been there many times, but I never took this kind of pictures. I don't have the equipment. So you're sitting down, it's sunset, you relax, you cool down, you have a cup of coffee or a beer or whatever is suitable and cool these days. Gin tonic, I understand, is the new vibe. And you switch your glasses from normal ones to infrared. What do you expect to see? You expect to see the heat, the infrared radiation that comes not only from the distant bodies, like those you see, the stars and the galaxies, but also all the heat that comes from the city. Let me do it again. You switch glasses to infrared, or even more convenient, you go on any website of ESA, NASA, any good agency, right? And you check the data from any of these missions, Herschel, or Gaia, or James Webb Telescope, recently making fantastic observations. And you see that you can read the infrared spectrum. You see how much info you already get from a sky that seemed completely flat before. You look at the sky with your eyes, no filters. It's a nice sunset, but it's all blue. You switch to infrared, and there you go. Lots of beautiful things already happen. It's not over with. Imagine you could see radio waves. Of course, the lower part is just a fiction, it's an animation. If you could see radio waves, you would see all the radio apparatus emitting, but you would see that your galaxy up there is also changing. You see it, maybe it's a brilliant day, maybe there's not much light in the buildings, you see a lot of stars, but if you switch to radio, you see deeper. Radio waves are longer, they're more penetrative, but they're also weaker, so there's a trade-off there. The picture you see up there is of a place, the Orgov Observatory in radio waves, which is not very far from where you've been the other night spotting shooting stars, right? Unfortunately, Orgov doesn't work anymore, but it's quite an impressive place. All these places, all these observatories are like that. They're big parabolas because they need to capture very long waves, right? And that's one feature. It's not over with. We can change glasses again and switch to gamma rays. And gamma rays are very powerful. So you see how deep, it looks like a painting from Van Gogh, right? This starry sky, right? And you see, every time we change glasses, we change energy, we change perspective, we add to our knowledge, but we're using our eyes all the time. Right? And of course, for a moment, I like to be Superman and see that I could see with X-rays, right? Or do all the cool things that Superman does. I wish I was looking like Superman myself. I'd have a lot more ladies around, but that's a different story. And with X-rays, you see, we can also shift to microwaves, the same waves that the oven uses to heat up your water. And you see that we go even deeper. Microwaves break up all the way to the dawn of time. And if you go on the, again, ESA website, you can check the data from the Planck mission. Let me zoom again, right? Deeper and deeper and deeper, past X-rays, past gamma. We go all the way down. And microwaves are relic radiation. It's traces of what we call the Big Bang, right? This initial explosion of matter energy that inflated the whole universe so quick. And that echo remains more or less at the temperature of the absolute zero, minus 273 degrees centigrades. What's common of all these different ways of looking at the sky? This is all electromagnetic waves. This is all electric and magnetic fields coupled together. They're the same, different energies, of course, as the light that's leaving the projector and hitting the screen to show you my slides. The same light that leaves the screen themselves. The same light that lets you see your mobiles. The same light you see with your eyes. Only, of course, there's only a limited part of the spectrum that you see with your eyes. A limited part, the wavelength. And you see to the left that depending on the wavelength of how frequent is the wave, how energetic it is, we have different phenomena. Radio, like I said, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma. You see how more frequent, how more compressed the waves are. This is an indication of energy contents. And whenever you see energy, you know there's also temperature associated. The higher the temperature, the more the energy we have of contents in a wave. But like I said, one dimension only, and that is visible, say, with your eyes, or with instruments that use the electromagnetic field. There's something missing then. You'll think about it. We'll get back to this question. And then you will tell me what dimension, what other thing that's so common in our experience in life is missing. You may wonder, say, well, the hell are you to talk to us like this? Why should we believe you, right? I thank very much for the introduction before. I got my PhD in physics between Italy and Denmark. I am a scientist for the European Space Agency. I used to work for the LISA Pathfinder mission, and it will be clear in a little while what it's all about. I'm now working on a strange mission to put clocks on the International Space Station to measure gravity in a different way, more complicated. I also teach. I like teaching a lot because I like to see students suffering when I'm giving them difficult exercises. No, not really. I teach orbital mechanics, rocket dynamics, all these things at the University in Madrid. So normally I teach in Spanish because my Spanish students are lazy. I told them, look, The language of science is English. We really should speak English, right? No puedo, estoy cansado, right? So, mañana, right? This is the philosophy. I love Spain as much as I love, teaching, so no big deal. In my free time, I also do other things. I'm doing some analysis for oil and gas, and that's fun because it's very similar to gravitational waves, it's just slightly different. But overall, I am generally a good man, so you can ask me questions and I'll try to answer. General relativity. You know a lot of it. There's one essential thought at the very center. And when you will work as professional scientists, I hope you will do, this is the perspective you always have to keep in mind. General relativity puts together the geometry of space-time with the contents in energy and momentum. So we lose the old description that comes from Newton in forces, accelerations, torsions, and all that, and we exchange it for, okay, maybe the universe, maybe a reality is just like a big plane, and normally the plane is flat. And whenever we sprinkle matter, or we move things around, or we push and pull, what happens is that we change the curvature, the geometry, and then things will move in the geometry of space-time as if going on a hike in a mountain, as if swimming in the sea. So the speed, the acceleration of things is a reflection of the energy, momentum, content that changes the geometry of space-time. Sometimes, literally, this is referred on the left-hand side as a stunning cathedral. This is all a beautiful construction. And you saw it in some of the formulas, some of these things with squares and, things that move. And on the right-hand side, we have all the complexity. Well, that is dust, that is a star in the end, that is us, Earth, with all its disgusting things, right? But it creates curvature in space-time. And in between, there's an obscure constant. It's a combination of constant, actually. And these are the two most important constants you have to remember when doing gravity. One of them is the speed of light, which is about 300,000 kilometers per second. Okay, so 1 second to get to the moon. And the other constant is the universal gravitational constant, which is even tougher, and I'm not even going to read it, but it's something that you really should remember. How Einstein deduces this, how does he get the constants right? Well, Einstein was Einstein, right? So I cannot really compete here. But there's a lot of history there, there's a lot of beautiful things to read. So when you have enough mathematics, you can go back and read things, and you will see that beyond the boxes, there's a beautiful theory that actually works up today against all tests we have run. So, but the big thing in Einstein equation, what you will extract out of them is the metric. The metric is the object that tells what lengths are, how to combine them, what speeds are. It gives you information on how the space is curved, right? And your professors have explained to you how to treat some of these simple metric, how to deduce the Lorentz transformation, for example, how to make sense of black holes. You've seen the Schwarzschild metric, and I mean, I've seen the slides, so you cannot cheat on me. I know what you know, right? And I also know what you did yesterday, and if you paid your taxes, I do know. No, don't forget this, I don't. Okay, but now, for all my slides, I would not need much of this. Just again, keep that in your mind. I mean, gravitational waves will be, in the end, small perturbations on this metric background. You hold that fixed, and you think, what if something was vibrating and propagating through space-time? Then we call it gravitational waves. But general relativity is fantastically successful, right? I mean, like I said before, you can think of space-time as a cloth, a big flat space, and you see that object now create curvature, See, for example, the big star at the end with the few stars around. And everything is bound to move following that curvature, like the light rays on the side. So you see that particles of lights, we call them photons, right? They are forced to fall freely, unimpeded, following the curvature. It's really like you going on a mountain. You have no choice. If you want to go up the cliff, you have to follow the path. It's not that you can think, I'd like very much to be there, and you think hard and you think hard and you're gonna get there. We don't have the power. I wish we had it at times, but yeah. So, and you see that in this specific case, the distant galaxy, right, emits light rays that get multiplied by these strange gravity curvature. And I can observe in the sky objects that seem to be following the rules. So the famous cross of Einstein, for example, you see I have a spot of light in the center, but these things are too regular and they're too static. So there's probably something in between the faults that changes gravity and that forces light to move otherwise. This is static general relativity, say. These objects are essentially moving so slowly I can think they're fixed. But even so, I see that space is warped. How about the dynamic case? You've all sat in front of the sea, right? Or in front of a big lake. And then you know there's two main effects. One is the local waves, those that come to you because of the wind, because of Earth rotation, because of the sun rising and setting, because of many, many reasons, right? So they're kind of frequent, they come and go, come and go. But there's also bigger wave effects, the tides. And you know that those are due to the moon. The moon goes around the Earth, and its gravity pulls the mass of water towards it. So you'll have ebb tide and high tide. And it goes up and down with a cadence of several hours, while the quick waves come and go to you basically one every second, every 2 seconds. But every wave is a wave. That's why we call them just wave. We don't have specific terms per different types. And a wave have a height on top of the average. They have a length, you see, between the two crests. And I can think that the frequency is the number of waves that pass through the same point per second. Gravitational waves are not different at all. This is the prototype of the type of gravitational waves emitted by a pair of neutron stars orbiting. You see, this is where I would need my hands. So I'll speak with louder voice. In this class, you will discover that neutron stars are like oranges, right? So this is apelsine physics, right? I let them rotate one around the other, right? And this is given, it's happening. There's objects in the universe that behave like this. And if you see, if I sit looking at the system in front like this, so the oranges, the stars, look and come and go in front of me, waves get generated in my direction, and they're very peculiar waves. They're emitted by any moving object, not only by our favorite stars. They travel at the speed of light, so they have no choice. It's not like a wave in the sea that can, come from a different phenomenon. Gravitational waves are traveling at light speed. The stronger the origin, the bigger are the waves. They're very, very, very tiny. So you're looking at a wave whose height on top of the universal flatness of space-time is like the size of a virus. And not even a big one, meaning the coronaviruses or big viruses like HIV are bigger than a gravitational wave. And you see how strange is that, right? The wave seems to stretch on the side well, they get thin on the other side. They get big and thin again. Big and thin again. So gravitational waves are very sad waves. There's no diet for them. They can't show up at the beach and be fully slim and perfect. They'll be fat and slim, fat and slim, fat and slim. This is called quadrupole or tidal behavior, and we'll explore that now in a second a little more. But the most important thing of all that I want you to bring home is that gravitational waves bring information of the system that has generated them. So if I have the two oranges spinning around and I observe for long enough the gravitational wave they emit, which of course is too small, it's not possible to detect, it really goes into confusion, but I'd be able to tell that those are two oranges. In the same way, I'm able to tell in the end that the two objects down there are neutron stars or black holes or maybe galaxies, you name it. Now, you see one more example. Think about these neutron stars orbiting around one another as the source of these perturbations in space-time. And you see that the space-time grid gets disturbed, right, by these ripples. And you also see below what the effect is if you put objects in space. Suppose you put a string of balls, right, little bits, and you see that the gravitational waves will shrink and enlarge the distances between them. This is their peculiar effect, and we can exploit it to detect and observe them. It's not that different than what you do again with your mobiles, right? When you switch on the Wi-Fi, we switch on the data, what you're doing is you're enabling the machine to receive waves that are emitted at a particular frequency by an electromagnetic emitter that you call router, or you even pick up the phone network. And gravitational waves require a different type of mobile phone to be detected. What happens then when a gravitational wave passes Earth? Earth is not just a string of little balls, bits, but you expect the gravitational wave to do to Earth exactly what it does to those suspended balls, right? So the wave comes, the crest is up, the mid, then down. So you expect Earth from this sort of sphere that it is to become then ovalized in the two directions. You see that this effect is strongly exaggerated. If I think that the diameter of Earth is about 12,000 kilometers, the passage of a gravitational wave would change it by about 1/10,000 times the size of an atom. So it's tiny, really tiny. You can imagine then that what we need to measure this vibration is a technology of incredible precision. And you see, for example, the wave is coming, is making my beds move, right? This is again strongly exaggerated. And I will need a very big size of this ring to detect such a small signal. And now you are a professional physicist. After this school, you know what to do. If we want to detect the variation, we do set a circle when the beds are not moving at their zero configuration. We put a reference system. You always do that in physics, right? Reference system before all. And you measure what is the extension in both directions. And you know that a gravitational wave has to shrink on a side and make things bigger on the other side. So while it goes small here, you see it goes big there, and the contrary, right? So I can form every kind of estimators that will tell me about the wave amplitude, and they will tell me that the one is in fact a gravitational wave. Another important ingredient that we need in this game is free fall. So if I think about this distribution of masses, if I don't have free fall, if I am not able to say that they're really just floating, I have a big problem of confusion between the effect of the gravitational wave and the effect of anything else, right? It can be gas moving, it can be the light heating up my system. So I will never have clarity on what's happening until I'll be sure that my little balls, that my detector is in full free fall. So what I do is I need to assure that. So take, for example, the case. Suppose you have 4 balls, 4 oranges that are falling towards Earth, right? So what do you think will happen? What will happen if I let those 4 things go? They will go down towards the planet. Is that correct? Yes, it is correct. Now, suppose you fix yourself at the center of those 4 balls, and now you let Earth fall on you. What do you think is going to happen? Well, what's going to happen is that the only effect you will notice is the shrinking and moving of the balls. So, vision number 1, I let them go. They go. Vision number 2, I let them go, but I sit in the middle. I have just changed my reference system, and I have taken away the standard gravity of Earth that's creating confusion. So you see, all you see in the end, all is left in the phenomenon, is the fact that 2 of the points are getting closer, shrinking, and 2 of the other points are getting far away, making themselves bigger. So you see, the effect of a gravitational wave is not very different than the effect of a body in free fall. Well, not all bodies fall in free fall with the same grace, right? Say, we all are what we are. So some people fall in pathetic ways. Enough with my talking. It's about time for the first experiment of today, right? So I will ask you to make a bit of space in the center and to give me a hand. This is called Larsen effect, the multiplication of 2 microphones. So this is not my mental to be Batman. This is space-time. I want you to hold space-time and make it pass, right? You need to make some space. Move aside, maybe stand up and move aside. Yes. I will really need your help. Stand up and move aside. Yes, yes, yes. I really need your help to... More? It has to be more stretched. Much more. You really have to, right? Okay. What's going to happen? This is space-time. It is flat, right? More or less. Keep it. Come on. What's going to happen? Yes. You can also use your hands. I mean, English is difficult, I know. It's going to come to me or it's going to go down? Go down. Interesting, huh? Does it all go down or only close to the object? Gravity is local. If I put 2 of them, anything different? Not much, right? And if I have smaller, oh, we lost the sun, bloody hell. One has to be careful these days with the price of oil. It's losing the sun. What happens if I have smaller bodies? Like coffee beans. You don't really see that, but if I go close you will see a little bump under each of them. And I can throw more coffee because coffee is nice, right? You see what happens to them when I throw them close to the orange, close to the sun? They fall. They get attracted. They are not attracted by the gravity of the orange because we see that, I mean, come on, I can hold him myself and he's not going to have any effect. But they are forced to follow the curvature of space-time. They have no way out. We have no way out. We're stuck. We fall in the gravity of Earth the same way. And this happens for all bodies, big and small, right? I can look for something intermediate, like a piece of chalk that will be maybe slightly bigger, right? What do you think will happen to light coming from one star? I have one star here, suppose, right? And light goes in straight lines, right? It radiates. It will go in a straight line. But the straight line is forced to follow the curvature. Maybe I'll use the other pencil. Sorry, guys. Oh, yeah. See? I have to go down. And if I go here, well, my light will be sucked in and probably eaten away by the orange. Oranges are not that good after all. What happens if I have two objects like I showed you before? I'm going to help them a bit, right? They're close and they orbit onto one another. What's happening to space-time? It's moving. And how is it moving? Like the sea. So what am I creating in space-time? The magic word. You know it. You just need to find the courage to say. Waves. Yes, sir. Waves. Waves are propagating from my system, which I'll try now to keep steady, but they're going to fall into one another, and that's okay, because eventually that's what's going to happen. Waves will be generated in this area by the two objects, and they're very, very strong here. But since they originate here, they will go wider and wider. By the time they reach the other end of the universe, they will be almost like a flat line. So you see that you can already tell which way they go, more or less. You could tell easily their ways. And I don't even need to show you what creates them, because now you see the effect. And even without seeing, you can tell me that these have to be rotating stars. Notice that while I'm creating waves, what's happening to all the objects in between? But how do they move? Do they leave their position? They just oscillate up and down, right? This is what happens with waves. They don't get to move their spot. Earth, you can think about the other orange, stays where it is. But it receives the wave and fluctuates. Now, the funny thing about gravitational waves is, and this is the limit of what I can show you here, is that what they're going to do to space-time is not only this, but also this. And this is this quadrupole effect I was telling you about. Now, the question is, how am I going to get rid of the coffee without losing the coffee? We can fold space-time. Why don't you let the apple fall, the orange fall this way? Hello, orange. What I just simulated here, what is this? A black hole. Very good, class. Full space-time. And send it back. This was just to have some fun before I tell you much more of what makes gravitational waves so spectacular. If space-time vibrates, we want to be dead careful and very clever at measuring its effects. So there you are, our beds are vibrating. So we build observatories and we use laser light. We have suspended mirrors at the very end. We know that space-time will vibrate the way you saw on the tarp. And then if I have a mirror here and a mirror here, and one big set of mirror in between, when this arm goes big, this one goes small. When this one goes big, this one goes small. Light is special. It can only fall in space-time. It can only follow those trajectories I've shown you before. And the beauty of light is that each photon particle is like a little clock. So if I send it back and forth like a tennis ball, the photon will then know the distance it's being thrown to. So it will know, once it gets back here, that that distance had been varied by a tiny bit. And once back here, that distance is smaller by a tiny bit. I match the two, and I get to know if that one is a gravitational wave or an earthquake or something local. Maybe there's moles digging holes or more complicated things. But anyway, this is the way it goes. We have many of them on Earth. We have many because we need to be sure that that's a gravitational wave. So we made the measurement in a spot, and if we measure the same thing in the other spot, we can measure the velocity of the wave, and if that's the speed of light and we have the same signals, then it's a gravitational wave. You see, the most famous ones at the moment are the LIGO observatories that are on the two side coasts of the United States of America. But there's also other observatories, Virgo in Italy and Geo 600 in Germany, and many more in the making. What do we do with measurements? Well, you saw before that the wave tell us about the phenomenon at the origin. And then it's easy to think, like you do for every phenomenon in physics, you can use the frequency in the low axis and put the deformation on the upper axis. And you can tell then which are the phenomena that the gravitational waves are bringing to you. Gravitational waves in this sense are like listening to an orchestra, right? You sit there, you can close your eyes, and since you have two ears, and since you've listened for that music, okay, that's the violin. It's down there. Yeah, ooh, that's beautiful. It really vibrates. Yeah, it's so frequent, there's so much power. And then you concentrate, that's the piano. Yeah, it's down there. Much deeper. And there's something beating. Oh, the drums. The drums are down there, right? Your ears are doing the spectacular operation of filtering and distinguishing each source per time. So the frequency C will see phenomena that last about 1 second, 1 minute, 1 hour, 1 day, 1 year. And what we call audibility, say your threshold of sensing from the ears, we call sensitivity curve for these instruments. Anything that lies above the curve is something you see or you hear. Anything that lies below is something that's invisible to you. So again, if people keep screaming at the orchestra, if people have their mobiles on all the time, you will not hear anything. That noise will cover the performance of the violin, of the piano, of the drums. But if everybody's quiet, then you can hear every nice sound. And the same goes in astrophysics. So back to the measurement. What happened in the night of the 14th of September of 2015? So we're checking the two observatories, the two LIGOs in Hanford and Livingston. That's what they look like. It's not surprising. They are big two arms observatories with the laser shining in. And over that night, we had something different. It's a little... This is the sound of gravitational waves. This is not a simulation. What was done is the extra vibration from the detector, the fluctuation in the laser, right, back and forth, was converted into a sound, putting the signal into an amplifier. So this is the vibration that the observatory in Livingston saw, and in Hanford saw, and this is the vibration that the observatory in Livingston saw. The distance between the two is compatible with the light speed. So these are the first two gravitational waves, actually the first gravitational waves because it's the same front, ever seen by mankind. The 14th of September, 2015. What are the waves telling you about? They're telling you about two black holes orbiting at the fantastic distance of 1.3 billion light years. The masses of the black holes are fantastic. One is 29 times the solar mass. The other one is 36 times the solar mass. And you see what they do, right? They're dancing onto one another. Waves are hitting the Earth until they join. Let me show you again, because this is very nice. Now, you of course have to realize that these black holes are so far away that this is not happening now. This was not happening on the 14th of September. This was happening 1.3 billion years ago. But the gravitational waves have been traveling through space-time. They're very, very powerful, although they're tiny, and there's no other phenomenon that can absorb them. And that's why we end up being able to detect them as a vibration on the surface of Earth. They first hit one of the observatories, then they hit the other one. We see this particular vibration, and we can tell that those are black holes. And there are two black holes, and you see we can tell the masses. And we can tell also that the final black hole is about 62 times the mass of the Sun. If you make the difference, 29 plus 36 minus 62, that makes 3. It means the power, the weight of this gravitational wave is about 3 solar masses. So it's enormous, it's fantastic. And the observatories can even tell you more or less where in the sky are the waves, right? This is not too difficult, right? I mean, again, you can make a quick experiment, right? Say, if you close your eyes, please. I got nothing to throw, so you can open your eyes, fine. The first sound came more or less from here, right? Where did the second sound come from? How could you say? Why? How many of these have you got? 2, right? Why? Because life is dangerous. There's damn animals out there that thousands of years ago were ready to eat us. And even now, I mean, it's not that easy out there. We are equipped with two sensors because then we can tell where noise is coming from. We're equipped with two eyes for the same reason we can tell distance. And also because in case one eye get damaged, the other one will work. In case one ear get damaged, the other one will work. Our brain is damaged anyway, so there's no hope for that. We gave a Nobel Prize. I mean, not I, but other friends gave a Nobel Prize to this. 3 people that were in charge of the ideas and the technology behind the LIGO experiment. And it's a very, very well-deserved one. Why can I say, for that particular type of wave, that that's black holes? That particular type of wave, this one, the one that starts very regular and then accelerates until it contracts and then dies so quickly, is called a chirp. A chirp, I'll tell you now in a second, is a very easy type of wave. And it is the wave that gets emitted by objects that rotate one around the other, also in the gravitational world. That is so because I can use again general relativity and predict that that's the case. But I can run simulations. I can put one object around the other. You see that the wave intensifies. It's really like, like a bird chirping, like a quick sound, right? This one is a simulation. This one is no measurement. The ones before were measurements. So this is us with computers trying to understand nature. The one before is nature. So the chirp, this type of wave, is like me clapping before, is like you going to listen for your favorite band, right? You can tell where the singer is, right? And you can tell what the players say. You can tell the speed of the end or the pitch of the voice. The information is encoded in the sound. It's all there. But it's also something more known, right? So birds are chirping. They're chirping all the time. So when you can drink your coffee in the morning, you can think now about the chirp of the birds, and you can think about gravitational waves. So I destroy morning for you all. Done. You have chirping also in unsuspected places. Check the windows of a building. Check them from any perspective. Those closer to you are bigger. Those farther away get smaller and smaller. If you measure these distances and put them on a graph, you obtain a chirp. Only the chirping of the windows, doesn't change in amplitude, while the chirping of the birds does. Enough with birds. This is incredible. We can apply that also to black holes, where the central black hole is a big monster. Say it's a watermelon black hole, or even bigger. I don't know if there's any fruits bigger than the watermelon. So, and then instead of our oranges, think about a cherry or a tiny seed, right? These are called extreme mass ratio in spirals. The ratio of the masses is extreme. It's David and Goliath, right? It's really, really big and tiny. And it's in spiral because we know, unfortunately, what's going to happen to the small mass. Check the wave below. Like a heartbeat. But it's getting more and more excited. Because the small mass is falling onto the big one. And it has to go faster and faster to try to escape. This is not conscious, of course. This is general relativity. This is gravity. This is nature. Faster and faster and faster. Unfortunately, it doesn't look good. Faster. You see the chirping? The frequency is going higher. What do you expect? The end should be really spectacular. You expect a fantastic explosion of incredible amplitude. See how incredible? And no, it's very depressing. Gravity is the weakest force in the universe when it's diffuse, but is the strongest when big masses are involved. So your chirp will always start regular because it is the result of the two masses, big or small, orbiting onto one another. This is a very regular orbit. But when they start spiraling, when they start going down, then the frequency will go, higher, and the amplitude of the sound will also go higher. Once they hit one another, once they become one, the process is basically instantaneous. This part is tiny in comparison to this part. So unfortunately, while we like science fiction movies and we know that we'd love to have a lot going on and fantastic explosions and big warships, gravity is very disappointing. It kills everything in a matter of half a second. The waves that LIGO have seen are altogether half a second in duration, those of the black holes. Okay, but then we can play again. Now please, do something for me. Do not go home and tell your friends and parents that black holes and neutron stars are oranges, otherwise my career is over. Black holes are black holes and oranges are oranges. In general, oranges are good for you and black holes are not. So stay away from black holes, but eat as many oranges as you can. Now, suppose I pick 2 oranges. This is homework for you, right? I'll do it now, but I want you to do it on your own. And I want you to do it with different ropes and different fruits. So I take a string. I took it very long so you can see the effect, but you can take it shorter. I'm taking 2 oranges. If you insist, you can also take 2 bananas, but they look less like stars, right? So you do what you want, right? But say, I don't want to sound, fruits, how do you say that? Fruits discriminating. I tie them to the string. Of course, when I did it yesterday, it all was perfect, and now it's going to be difficult because it's in front of you. So the trick of the string is a trick because I cannot hold the oranges up without having them fall. If I was in space, I could try this trick without the string, but it still would take a much longer time. The string saves us the time because it simplifies, it transforms the conservation of angular momentum to what I want to show you in gravity. Almost done. Okay, now, this is my binary system. This is my stars. And I can let them gravitate one around the other. Now you see, the closer they get, the faster the orbiting period becomes. I'm using the string to enhance the trick, right? But you see faster, faster. If you measure, and you could actually use your wristwatch to measure the orbiting period, you see they go faster, 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 faster. What do you think the animal's going? Yeah, I'm afraid. This will be a big orange juice, yeah. Poop. You see how quick they get in the end. And of course, if it's neutron stars, if it's astrophysical objects, if it's black holes, you expect them to become one. It's trickier if you want to use the mathematics, if you want to use numerical simulation, it's complicated. Well, here you see, thanks to oranges. Oranges are really good for you. There's no objection to that. Let me see if I can use a different trick to enhance the phenomenon. You see how nice it is? The oranges keep turning even if I don't watch. Let me repeat this without the other trick. I want to give it more momentum. You see, I don't even have to choose an exact orbital rotation. Now one is a little steadier and the other one goes around a little faster. It doesn't really matter. They will speed up until they eventually collapse onto one another. Exercise. Build your own orbiting oranges system. Take measurement of the period and how it changes. Verify that that's a chirp. And at the question and answer session, you'll show me or you ask me questions, or right? Right? Da. God. Do you guys speak Russian or what? Thanks to LIGO, black holes are not science fiction anymore. And now oranges are segregated in apples and they become much pricier in supermarkets because everybody wants to do the same experiments. Before LIGO, you would only eat oranges and apples. Now they're chased by every physicist worldwide to make experiments like mine. The power of the detection of gravitational waves lets you see not only what they're made of, two black holes, what masses, they also let you see where are they from in the sky, more or less the angular distribution, and also the distance. This is because in the amplitude of the waves, there's a crucial information, which is called the luminosity distance, that tell you step by step, more or less, where the objects are, what the distance of the object is. So these are the first observations by LIGO. You see not only the one of the 14th of September 2015, also 26th of December and 4th of January 2017 and all that, and they're further and further because LIGO had time to integrate the signal. You see that every observation in the sky is very blurry. So yeah, I'm sitting here, I am LIGO, my arms are vibrating, I'm detecting gravitational waves, and I see a signal, a chirp. Okay, that bird, that gravitational bird is down there. Only that those two stars sing, and have been singing for me for half a second. And when somebody calls your name in the market and it's just very low for half a second, you cannot tell what the person is. I know that my friend is there because she or he said it will be there for me, but no way I can tell. So you see how the distance, the angular distribution is very vague, right? You see how big it is. This is all the sky, all the sphere around me, and I can only tell that that's about down there. But there is a signal that seems to be more localized than the others. This is nicer. Do you know why? Why is it that that particular detection gives me a point much more localized, much better? Do you know why? We said that for the black holes, this is about 0.5 second long. But if we're so lucky not to deal only with black holes, but to detect neutron stars. So this is a black hole and a black hole orbiting. So in this plot, black hole and black hole, very strong objects, very strong gravity. Neutron stars are stars. So if you see them from afar, it's the same picture. But these are stars. Say, okay, you can even orbit around them. They're not so dangerous. Then you will see the same vibration. And then, of course, it will become a chirp. But this is much longer. This is minutes. If you're lucky, it can be 10, 20, half an hour. When you have so much time to listen, you can tell where your friend is with much higher precision. The friend was on the other side of the market and he's been calling your name continuously. Hey, here I am. Hey, here I am. Instead, the black holes do say, hey, and then they go, right? They're very unfair, right? But of course, we're very unfair to them because we call them black holes and they think they're the dump of the universe and that all mass fall in. They have a very, very bad name, so I can't blame them. But fine, okay. Let me tell you more about all the detection that LIGO has gone through. So it's hard to see because the screen is small, but you see all these objects are the same, they're similar. I'm not even telling you if these are black holes or neutron stars. You see that all of them develop chirps. Some of them are very high amplitude. And when they die, when they collapse onto one another, they all do the same. Let's zoom in on the one of the 14th of September. Wave, wave, looks like a lullaby. It is not. They get closer and closer and closer until they merge. Okay, this one is half a second. So now I really exaggerated that. But there are signals that really last a long time. This is neutron stars orbiting. The noise you hear will intensify. When you have so much time to listen or to observe a phenomenon in the sky, right, you have the advantage of pointing its position. Now, gravity is very powerful because while light, radio signals, infrared, all these is the electromagnetic spectrum and you can shield it, right? That's why when you go up in the atmosphere in your plane or you enter a room which is largely made of metal, your phone doesn't work. It doesn't work because all these electromagnetic fields are shielded. You cannot shield gravity. You can go up one floor, you can go down one floor. Mother Earth is asking you down. And the Earth is falling in the sun. And the sun is falling towards Hercules. And on and on and on. You cannot shield that. It is not that being in this particular room makes gravity null. The only way to make gravity null is falling. But if I fall from too high, dangerous too. So the fact that I do receive the gravity information regardless gives me time to tell the other instruments that see in the electromagnetic spectrum to point their eyes straight there. So what's happening is I'm getting the signal of gravitational waves and a few seconds maximum later I'm getting the electromagnetic waves. So LIGO gives me the signal, and if I am quick enough, the moment I get a detection, I'm going to tell all the other spacecrafts that do check in the electromagnetic fields, all the telescopes, all the satellites, to point, to orient that way. And then I'm going to get a gravitational signal and an electromagnetic signal, and I can do wonders when I have both of them. Another incredible thing that happened after studying the neutron-star merger is that since we can tell about the masses involved and we can tell about the elements and how they change, now we can tell how the masses are composed, what's very likely to be in there. And we understood that from neutron-star mergers in orange, lots of elements are created, lots of the heavy elements that before we only thought were due to dying stars of low mass. So analyzing gravitational waves give also a lot of information about elements in the universe. And of course, makes Mendeleev very happy. So it's a big party in Tobolsk. Now, I don't know if you've ever been in Tobolsk, the place where Mendeleev was born, right? Tobolsk is a frozen place in winter just north of Tyumen. So this is the Trans-Siberian, this is Tyumen. I'll use Latin character because it is easier. And this is Tobolsk. And Tobolsk is about 4 hours by standard train above. Now, when the Trans-Siberian Railway was constructed, the Tsar, the engineers who were in charge, offered to Tobolsk, which was the big city back then, that the magistrali, the Trans-Siberian, would pass through there. And then the old guys in Tobolsk were talking to one another. Lots of vodka, of course, and rice. And they said no, because they thought that the big train coming would ruin their economy. We don't want that. That's change. So what happened is that the Trans-Siberian was then built 4 hours lower, right, passing by Tyumen. Now, Tyumen is a big city with lots of commerce, lots of transfers, a beautiful economy, and Tobolsk is dead. So when you listen to people, keep both ears on, right? Anyway, that's Mendeleev for you. With me in March 2015, it was minus 15, I think, and it was a lot of fun going to Tobolsk. Have you thought about what I asked you before? Electromagnetic waves, infrared, ultraviolet, radio waves, you using your eyes, right? What have we changed? What was missing that we now have introduced by using gravity? What are we using to observe the cosmos?
Exact gravitational wave bodies, because our bodies are also moving bodies.
That would be lovely. It would be fantastic to do, but it's very, very much weak. We cannot do that. We cannot because we're not sensitive enough, right? But what are we doing instead? Say we build the instruments. The instruments are doing that for you, but are we using only our eyes to inspect the results? Or is there something else we are using? We use ears. So your universe, until gravitational waves were discovered and used, was like a big picture, beautiful, colorful, but something is missing, right? Now we know a lot more about objects that populate this beautiful universe and that are not visible by us. So I don't want you to go home and tell the Professor Armano has told you the gravitational waves are sounds. No, they're not. But when we observe a scenario, we were stuck before by only what our eyes could see, only to electromagnetic waves, electric and magnetic fields. Now we can use gravity that tells a lot about objects that live in the universe and they do not emit any light. So this is essential and essentially beautiful. A few comparison energies, because we are physicists and we are proud of it. If you think about the Hiroshima nuclear bomb, it's not a very pleasant thought, but I'm asking you to think about it for a little while. Well, the mass it was converted to energy was only 0.7 grams. And that destroyed cities, right? If you think about the Starship Enterprise, are you a fan of Star Trek? Do you like Star Trek? Well, maybe it's more for my generation, right? Well, the Star Trek Enterprise, the ships are capable of warp speed, right? So they warp space-time before and after, so they basically don't move, they just shift, they displace in space. But they're also capable of impulse power. Impulse power is driven by fusion reactor. We don't have fusion technology yet. I hope we're gonna get it soon because it's beautiful and it's needed. So 10% of the mass of the fuel, the Enterprise, will be required to push it up. So it's 600 million kilograms of fuel to move the ship. What do you think the LIGO radiation is about? How many zeros shall I put in kilograms? Yeah, somebody knows, of course, but yes. A lot of zeros. So this is the amount in kilograms that was emitted in gravitational waves on the 14th of September 2015. Well, that was detected by us. It was emitted billions or millions of years ago in that distant system. And what we're going to study in the sky, when we'll be able to build the new observatories, are phenomena that are even more striking. So a supermassive black hole mergers of millions of solar masses will have this number of zeros. And we're sure we're going to see that. It's not an estimate. Now, this is a bit of a complicated graph. I want you to think about what I told you before, that in this particular type of cosmology and astronomy, we put frequency on the horizontal axis. So how frequent are the waves coming, how energetic are they? And in the vertical axis, we put the strain, the amplitude of them. So you see, the frequency tells you to which phenomenon you're referring. And there's something kind of obvious about it. There's only that much that we can do on Earth. Earth is shaking all the time. It sticks us to the ground. There's a lot of effort. You see what kind of trick I have to employ to make you understand neutron stars. I have to use wires. I have to use tarps with things. And this is not science, but it's trivial, right? If you want to do real science, you have to go and build experiments. This is the maximum the LIGO can go. It can go down to seconds. It means that the maximum phenomenon you can see is this chirping waves, 1, 2, 3, 20 seconds, half an hour, maybe maximum. If you want to explore the gravitational sky, you really have to go to space. There's other ways, but going to space is the safest. So how you do that? Well, since LIGO is so successful, you build it in space. In space, you do not need to have your mirrors at the end anchored to points. You can have them freely floating. So you can put satellites far away, one away from the other, as far as you want. The concept is called LISA, Laser Interferometer Space Antenna, or LISA as they say in the US. The length of the arms is 2.5 million kilometers. So it's really, really a lot. LISA will behave exactly like LIGO. Say, when a gravitational wave will pass, you expect the constellation to breathe, to become bigger and then smaller, exactly along the two directions. So if I get fatter, I also get shorter. If I get thinner, I also get slimmer. Right? So you see, when the wave passes, depending on what type of wave, you will see that the distances change, and you can tell that it was a gravitational wave. Again, even on such a powerful instrument with 2.5 million kilometers side, the change will be a fraction of a diameter of an atom, which is comparable to measuring the thickness of a piece of paper on the distance between us and Proxima Centauri. Proxima Centauri is the closest star to us, is the one we would like to travel to if it was possible, and it's about 4 light years away. So it means it will take 4 years to get there, traveling at light speed. What do you put LISA? Okay, you launch it. LISA will form a triangle. Remember that I am showing you the laser line in red, but that will be invisible. So all you will see if you point your telescope is 3 objects in an equilateral triangle formation, 2.5 million kilometers apart. They will be following Earth, you see, shifted by about 20 degrees, because then we have less noise, we have better communication, and lots of different pluses. And you see that the constellation will have these strange cartwheel type of motion, which is given for free by Keplerian mechanics. I mean, we don't have to control it. And while it moves, the constellation will do what your ears do. So your ears are fixed around your head, thankfully. But if you know that what you're listening for is a phenomenon that's constant in time or that stays there for a long time, you could think about parking one of your ears here and then putting the other one here. Or using the same ear, you move it from here all the way around and you listen for the same phenomenon from different points and you can tell where the angle in the sky is. Why LISA? Well, because this cosmology is just fantastic. With gravitational waves, we can explore the Big Bang. Because the Big Bang happened with no light. The matter was so dense, was so thickly packed, that there's no way light can escape. It's worse than a black hole. Yeah, we found something worse than a black hole. Cheer up, right? And gravity comes before light. You can tell a lot about what happened there. You expect gravity to come with similar signals to the one I showed you, and it will tell you a lot about the source again. What happens at the horizon of a black hole? A black hole is a damn object. I mean, we have something happening in between, but we do have the Schwarzschild radius, right? And the event horizon that, depending on the type of black hole, is the Schwarzschild radius are different. And whatever happened after here in between, all the way inside, we don't really know. We have a few ideas, but yeah, but we don't really know. There's no measurement. What's the role of dark matter? If you write down Einstein's equation and apply them to an isotropic universe, that is, you think that the universe is like the black cloth I told you, only with coffee grains, and then you try to deduce how gravity behaves, you discover that more than 70% of it is actually matter you do not see. There's something dark, something invisible, that makes things move and rotate. But we've been following this idea of dark matter for many, many years. We don't really have any credible measurement based on gravity. Gravitational waves will tell you about it and a lot more. So the observation of gravitational waves is key. You see, they escape the Big Bang. They can tell you something about inflation, the recombination when particles are finally free to combine and form structures, to today. They can tell you about how black holes evolve, because a black hole is not born big. A black hole gets big because it swallows matter, or because it swallows other black holes. So I will have a zoo of different waves, different chirps. We start having it, right? Depending on how big they are. Some of them are really small and tiny. Well, then maybe then is a small black hole that's a big black hole. And the distribution in the sky is not that different. Maybe they belong to the same family tree. And it's possible to establish a family tree of black holes that tell you in a way how space-time has evolved. Because the bigger the black hole, the older the black hole, typically. And then if you put them all together, I want you to think about the orchestra, right? Well, they form what's called the sensitivity curve of LISA. And whatever is above, we measure. Whatever's below, we don't. LISA is a complicated piece of technology. So we were not sure years ago we could build it. And LISA is expected for 2034. So it's starting to become an item now. We had to think about it earlier. So between 2003 and 2015, we built a technology package, a demonstrator that would show that LISA was worth it. How did we do that? We packed two of the laser LISA inside one spacecraft that you see now exploded, but that normally would look like the space between this particular stand and those tables there, round about this height. And we sent it to space. This is not a detector of gravitational waves, it's too small, but it can prove all the ingredients we need for LISA. If you zoom in, you see that you have lasers, an optical bench, and two mirrors of very particular nature that look like cubes. And the laser shines in between. And once they fluctuate, we let them go. They have no contact. And we have a lot of experiments on board to prove that they're in fact in free fall. And this technology is the very same that will fly on LISA to detect black holes and neutron stars and cosmic microwave background and all that. This is how we mounted the spacecraft on the top of the fairing. And you see it gets closed in the fairing itself. This is at the integration center in Kourou, French Guiana. You see how quickly people move there. It's incredible. You get bolted, get lifted up. It's like surgery. Bring out, take some sun, slowly, gently. Get brought to the launch tower, where there's a Vega rocket waiting for it. Initially, we were bound to use a rocket, a Russian launcher, but in the end, we had to use a Vega because it was easier technology for us. Right? Gets ready, gets out, and we're ready for launch.
9, 8, 7, 6, 5, 4, 3, 2, 1, top, allumage et décollage de VV06.
Takeoff happened on the 3rd of December 2015 at 4 a.m. European time. Vega is a very quick rocket. You stop seeing that rapidly, but this was exciting. We raised the orbit 6 times because we need to go to a special point of equilibrium between the Earth and the Sun. It's called a Lagrangian point. It's the point where force is null, including acceleration of say, centrifugal acceleration. And then we have to orbit there for a lot. We stayed there for 1.5 years. You see, it looks like a potato chip. It took us 50 days to go there for launch. We removed the propulsion module on the 2nd of February, and the final orbit you see is gigantic. It's 500,000 kilometers times 800,000, with an orbital period of 6 months. And what did we do there? Well, we simply let the masses go. Now, of course, they're not alone. They're surrounded by all the electronics. They're surrounded by their own caging mechanism and all the spacecraft. But the idea is leaving them go as much as possible because that's what LISA will need. 3 mirrors, like in LIGO, to detect tiny fluctuations. And we've done a lot of physics there. on free fall, on control of charges, on cosmic rays and magnetics measurements. This is complicated for the scope of the lectures. If you're interested, we can talk about it either during your campfires later or during breaks, as much as you like. Now think about this curve I showed you. You're only as good as your ears. If your ears are good, you listen for a good orchestra. If you don't, you don't. The ears of Pathfinder proved amazing. If this is where you need to be for your LISA requirements, remember this is frequency and this is the gravitational universe you want to see, right? Whatever is above, the signal coming from neutron stars, black holes, the background of the initial Big Bang, all the phenomena. If we make it to make an instrument this beautiful, then we'll see. Otherwise, we won't. This was what Pathfinder, what LISA Pathfinder was supposed to test. So it's as if, okay, you're going to the concert, but you don't understand about classical music. Just, enjoy the violin. I was told it's good. No, we got the full orchestra. This is our signal measured. It means that we can build a LISA better than the LISA we initially thought. We will see and hear much more of the cosmic concert than what we initially planned. So all the science of LISA can be done. In poor terms, if you had to make one comparison, it's as if we were able to weight the mass of one bacteria, one little virus, on top of one of the masses. This was the level of precision that we got to. Or, if you want again, we measured the size of a human rhinovirus, imagining it got its weight on one of the test masses. Pathfinder was an international success. This is the award ceremony in 2017. I am standing here with a stupid face. But I do always have nice ties. I mean, today I really was meant to wear one, but it's too hot, so maybe another time. And for me, it's a fantastic team of colleagues and friends. I hope I managed to pass a bit of the idea of gravitational waves, what they're all about, how do they behave in space-time, why they're so fundamental, why they give you so much information, why it is worth to study them. For the rest, check the ESA website on LISA, which we're going to launch in 2034, so you have plenty of time to study physics, get your PhD, and come to work for us, of course, because we want you, and to get involved. What about the future?
We are approaching the perimeter. I'm picking up the gravitational wave fronts.
Engage forward shields, 35%.
Shields up.
Drop to 1/4 impulse, Ensign.
Yes, sir.
Captain, gravitational wave front intensity is increasing steadily. 1100 standard G units and rising.
So Captain Picard is confused. He doesn't quite understand why gravitational waves are there, and Worf is helping, and Riker is doing the Riker thing, that he's looking cool and sitting down. We all have our roles in front of gravitational waves. The best thing we can do is observe them. We hope in the future to have instruments able to detect them as easy as on a spaceship. Meanwhile, Spasibo Bolshoya, thank you very much for your attention. And if you have questions, meanwhile, Lisa will unravel in front of you.
I didn't understand how the gravitational waves can help us to learn something about Big Bang.
Thank you. A very good question, actually. The Big Bang is a moment of very strong expansion of mass, right? In a very tiny amount of time, we think the Big Bang is a high conglomerate of matter. Matter is all there, compressed in one point. And then, boom, it becomes bigger. We don't know how it becomes bigger. Maybe it becomes bigger as a potato, maybe as a sphere, who knows, right? But there's a big change in the mass distribution from one point quickly to larger and larger spheres. This strong change of mass distribution generates gravitational waves. Very, very strong ones. But those waves have been there for 12, 13, 14 billion years because they've been there all the time with the universe expanding. Like for black holes, when with LIGO you see the chirp and it tells you, oh, there's two black holes, they're getting together, they're orbiting. And you can tell so much from the waves, so much we should be able to tell about the black hole if we can detect the waves that come from the Big Bang.
If Big Bang is so strong, why did it appear?
It's a very good question. Big Bang was so strong, but when it happened, all the matter of the universe was compressed into one single tiny object, right? And that's all that was. But that boom, that bang, expanded at light speed. And now we have it from other astronomical measurements from the most distant object in the sky, that the universe is probably about 13, maybe even more billion years old. And you can compute the distance, right? It's really huge. So the boom, the power of that explosion is now diluted into a gigantic space. So your coffee was very strong in the morning, and now somebody poured your coffee in the ocean. And this is the task, right? The task is finding the taste of that coffee in the ocean now, in the big universe we have, and being able to tell what coffee beans coffee is made of. I don't know if the comparison is helping you. Thank you guys.